Hello everyone. Today I'd like to show how to create a simple 3D renderer using a technique called raycasting. Raycasting is a method of rendering objects by sending rays from the camera through each pixel and calculating where they intersect with objects in the scene. To find these intersections, we need to use mathematical formulas. I'm going to write this raycaster in GLSL, which is a shader language that runs on the GPU. Let's start. We are given the coordinates of the current pixel. If we divide these coordinates by the screen resolution, we get normalized coordinates from 0 to 1. These coordinates are called UV coordinates. We get a gradient where red represents the x coordinate and green represents the y coordinate. The bottom left corner is black, because both coordinates are 0. The bottom right corner is red, because the x coordinate is 1 and the y coordinate is 0. The top left corner is green, because the y coordinate is 1 and the x coordinate is 0. And the top right corner is yellow, because both x and y are 1. The center has a value of 0.5. To make the direction face forward from the center, we need the center value to be 0 instead, so we can simply subtract 0.5 from the v coordinates. We also need to multiply the x coordinate by the aspect ratio to prevent the image from being stretched. To create a ray, we need two things, a ray origin and a ray direction. They can be created using this code. The direction vector should have a length of 1, so we normalize it. Let's visualize this direction as a color. The XYZ values correspond to RGB colors. If we look along the positive X direction, we should see more red, which is what happens. If we look upward along the Y-axis, the color becomes more green. And if we look forward along the Z-axis, we see blue. If we look in the opposite direction, we see a black octant, because the values are negative there. I have created a ray structure to store its origin, direction, hit position, hit normal, hit material, whether it hits something, and the light source. I have also created a material structure that stores its color, diffuse, and specular values. And I have created a light structure that contains its direction and intensity. I will not explain how to find a sphere intersection in this tutorial, but you just need to solve a quadratic equation. Here is the solution I came up with. If the discriminant is negative, there are no intersections, so we simply return the ray. The ray should not travel backwards. Therefore, if the calculated distance is negative, we return the ray. The hit position can be calculated by adding the ray origin to its direction, multiplied by the distance. The normal is calculated by offsetting the hit position by the sphere position and dividing it by the radius to normalize it. Then we set the ray hit value to true and return the ray. To find the closest intersection point, we need this function, which simply returns the nearest ray. Now we can set up our scene. I have created white and green materials, created a sphere with a radius of 1, and assigned the green material to it. Now we need to set up the ray, pass it to the raycast function, and visualize the material color. As we can see, the sphere is green, but it lacks shading. Let's visualize its normals. We can use these normals to shade the sphere. Simple diffuse lighting can be calculated by taking the dot product of the normal and the negative light direction. The dot product tells how similar two directions are. If the normal is facing the light, the dot product is equal to 1. If they are perpendicular, it is 0. If they're facing opposite directions, the dot product is negative. So we remove those values by taking the maximum with 0. Now our sphere is shaded, but it is missing a specular highlight. Specular shading also uses the dot product, But first, we need to reflect the ray direction around the surface normal. Then we raise it to large power to make the highlight smaller. Here's how it looks. Now I will add a plane. Here's the intersection function. Here's how it looks with the plane. The sphere is missing a shadow cast on the plane. We need a function to calculate which pixels are in shadow. First, we check if the normal is facing away from the light direction. If it is, we don't need to calculate the shadow, because we already have a diffuse shadow. Then we offset the ray by a small amount to prevent it from intersecting with the same surface point. After that, we cast the ray towards the light source. There is a shadow if it hits something. Now we have shadows, but they look too dark. To fix this, we need to add ambient light and the sky. Ambient light uses the dot product again, but we change its range from -1 to 1 into a range from 0 to 1. Then we multiply it by the sky color and the material color. To create the sky, we simply change the color to the sky color if the ray does not hit anything. It looks brighter now, because we have added several types of shading. However, the brightness can be greater than 1, which causes clipping. To fix this, we need to take these colors and tone map them into the 0 to 1 range. For this, we can use this tone mapping function I created. Now it looks much better. I will add fog to remove this harsh line on the horizon. I normalize the ray distance by dividing it by the maximum distance, and use this factor to mix between the object color and the sky color. And here is the final result. Thanks for watching. Until next time.